So now by assumption, we are using the fact that in linear algebra, if you have simultaneous eigenstates or eigenvectors of some Hermitian set of commuting Hermitian operators, they form a complete orthonormal set. So that means that by assumption, I'm using the notation that if I have a vector psi lambda m, I'm using this for that, right? Now, what about its Hermitian conjugate? For that, I will use the notation this. Okay, so this is called a ket, and this is called a bra, so that the whole thing together is a bracket. Okay, so by assumption, orthogonality or orthonormality tells us that if I take psi dagger lambda prime m prime and take its inner product with psi lambda of m, that is going to be delta lambda lambda prime. This is a Kronecker delta times delta mm prime. So this we write as lambda prime m prime lambda m. So this is the bracket, which is an inner product. And this is lambda, delta lambda lambda prime, delta mm prime. Okay. Now for a given irreducible representation, for a given E-rep, lambda is fixed. Okay. So for now, we shall only change m. So for now, what we are the relationship that we will be using is that the lambda is the same, m may be different. So we have m prime. Okay.
Sir, I didn't understand the statement for a given irreducible representation lambda is fixed.
Yeah, because of Schur's lemma. Schur's lemma tells us that the eigenvalue of the Casimir operator is fixed for a whole representation, irreducible representation, right? Here, let me explain. You have j squared, which is a Casimir operator. It commutes with all the operators of my Lie algebra. So that means that by Schur's lemma, on an irreducible representation, j squared has this form. So if I concentrate my attention to an irreducible representation, this eigenvalue cannot change, right? Okay. Is that clear, Nahi?
Yes, sir.
I mean, I think it'll become clear for you because at some point in the near future, your physics intuition is going to kick in and you'll see that lambda is nothing but the square of the total angular momentum eigenvalue. Okay, so this is basically what we want to use, this orthonormality relationship. We will use this quite a bit. Okay, so now, we want to find what C and D are. They will allow us to find the whole representation. Okay, we want to find C and D. You might say, oh, they're just proportionality constant. Why are they so important? You will see that they are the key. They allow you to build the matrices explicitly, and we shall do that. Okay, we want to find C and D. So let's apply J plus on lambda m. This, of course, increases the m eigenvalue by 1, right? So if I were to take an inner product with another state and wanted the inner product to be non-zero, what should be the eigenvalue I should put here? I want this to be non-zero.
M plus 1.
Right. So I want that to be m plus 1. And so, so this is what I want to compute. But we know that J plus acting on lambda m is C m plus 1 lambda m plus 1, right? But this is just a number, so I can factor it out. So I have Cm plus 1. It's a complex number in general. And then we have lambda m plus 1 lambda m plus 1, the bra and the cat. By orthogonality, this is just 1. So we see that this is Cm plus 1. So Cm plus 1 is equal to the inner product between lambda m plus 1 and J plus acting on lambda m. Okay? So now let's look at D. So we got D by applying J minus. So J minus acting on lambda of m is D of m lambda, sorry, D of m minus 1, right? D of m minus 1 lambda of m minus 1. Now, what if I apply J plus on lambda m plus 1? Then I will get D of m here, and here I will get lambda of m. Now, if I take the Hermitian conjugate of this whole equation, what do I get? I get lambda m plus 1, the bra. The Hermitian conjugate of J minus is J plus. And here I will get lambda of m, the bra, and then D star of m. But D star is just a number, so I can bring it forward. I can just write it wherever I want to, okay? Now I want to have this equation acting on some ket, some vector. So what should I put here so that this is non-zero?
M.
Right. Because, yeah, very good. So we get m here. So on the right hand side, I will get D star of m, lambda m, but this is 1. So we get D star of m as lambda m plus 1 J plus lambda of m. Okay. So if I now go back and check our expression for C, let me take a copy of C and bring it down here. What do we see? We see that C m plus 1 is the same thing as dm star, right? Okay, so only one set of proportionality constant is needed. The other ones we get for free. Okay? The other ones we get by complex conjugation.